It is late. You've got your IDE open on one monitor, a terminal window blinking away on the other, and you are just staring down an architecture problem that feels like a massive brick wall.
Oh yeah, we have all been exactly there, just staring at the screen.
Right, because you're trying to build an AI system, and you've hit the glass box of the large language model, the knowledge cutoff.
It is, honestly, the defining frustration of modern system design.
Yeah.
I mean, you have this massive neural network, right?
Yeah.
And it's capable of parsing complex logic, refactoring code, synthesizing all these ideas, but, well, its memory is basically frozen in time.
Frozen at whatever date it finished training.
Exactly. It only knows what it was explicitly trained on up until the moment those training weights were totally locked. It doesn't know about your private GitHub repos.
Right, it has no idea.
It doesn't know about the API deprecation that literally happened this morning.
Yeah.
And it definitely doesn't know your company's highly specific, usually undocumented business logic.
Yeah, which is the worst. So you ask your custom model to, like, debug an outage that happened yesterday, and it just confidently hallucinates a fix that makes absolutely zero sense.
Or you ask it about your internal code base,
Yeah.
and it spits out a generic tutorial from, like, 3 years ago. The model is brilliant, but it is effectively trapped in a static snapshot of the past.
So how do we break the glass box? We use RA, Retrieval Augmented Generation.
Yes, the big buzzword.
The buzzword, but also the real solution. It is essentially giving your AI a library card. It completely shifts the paradigm from the model taking a closed book test strictly from memory to taking an open book exam where it can, actually look up the answers.
That's a great way to put it. It moves LLMs from static snapshots to dynamic, verifiable knowledge engines.
Okay, let's unpack this.
Go
Because
ahead.
as an engineer, giving it a library card is a really nice whiteboard concept. But I want to know the actual mechanics here.
Like the under-the-hood stuff.
Exactly. When a user actually types a prompt into a RG-enabled application, what is physically happening to inject that outside knowledge before the text even generates?
Okay, so let's trace the actual data flow. When the user submits a query, your application intercepts it.
Okay.
Before that query ever touches the LLM, the system takes the question and queries an external database. Your library, basically.
So it's stopping the prompt in its tracks.
Exactly. It pauses and it searches for the specific paragraphs or wiki pages or code snippets that actually contain the answer to the user's question. It retrieves that raw text.
And then what?
Then, your system takes those retrieved documents, stitches them together with the user's original question, and constructs a single, massive new prompt.
Oh, I see. So instead of just sending the raw prompt, like, how do I configure this specific internal router,
Right.
the system dynamically rewrites the prompt to say something like, here are 3 pages from the router's current instruction manual retrieved from our database. Based entirely on these pages, how do I configure this router?
That is the core mechanism right there. You inject the context directly into the working memory of the model, its context window, right at the very moment of generation.
Grounding it in reality.
Exactly. You ground the model in your current verifiable reality before it even has a single chance to guess or hallucinate.
Okay, so we've injected the context and the hallucination is theoretically gone. But, I mean, there is a physical limit here, right?
Oh, yeah, absolutely.
You cannot fit a 5,000-page API documentation PDF into an 8K context window. The API will just flat out reject the request.
Right, you'll just hit a hard token limit.
So we have to find the specific pages that actually matter? How are we deciding which 3 pages actually make it into the final prompt?
Well, finding the needle in the haystack is where the engineering really gets intense. Because there's a rigid 5-stage pipeline that happens before the LLM even wakes up.
Wait, 5 stages?
Yep. Query processing, embedding, search, ranking, and selection.
Wait, hold on. 5 distinct stages. I really thought we were just doing a database query and calling it a day. What is adding all that overhead? Let's walk through it.
Okay, so a simple query will almost always fail because users rarely ask perfectly formatted questions.
That's the truth.
Right. They use slang, they omit context, they just type random fragments. So stage 1, query processing, fixes that. If a user types fix auth bug, the system expands and rewrites that query into something much clearer, like auto 2.0 token exploration error resolution.
Oh, so it's translating human lazy speak into system speak.
Basically, yeah. Then stage 2 is embedding, We translate that expanded text into high-dimensional vectors.
Which usually just gets glossed over in tutorials as like turning words into numbers.
Yeah.
But we aren't just assigning arbitrary IDs, right? We're mapping semantic meaning into space.
Exactly. We're mapping concepts into a mathematical space, usually with like 1,500 dimensions or more.
That's a lot of dimensions.
It is. And in this case, the vector for the word router and the vector for the word firewall end up mathematically clustered together because their semantic contexts are very similar.
Yeah, I follow.
So when we move to stage 3, the database calculates the distance between the query vector and all the document vectors. It pulls the documents that are mathematically closest, even if they don't share exact keywords.
Right, so it knows what you mean, not just what you typed. Okay, so we've searched and pulled a list of related documents. What are the last 2 stages?
Well, stage 4 is ranking. Fast vector search is great for pulling, say, 50 broadly relevant documents really quickly, but it's a blunt instrument.
How much noise?
Way too much noise. Ranking often uses a secondary, heavier model, usually called a cross-encoder, to read the query and the documents together, scoring them for true, nuanced relevance.
Oh, so a second AI is grading the search results.
Exactly.
Yeah.
And finally, stage 5 is selection. The system looks at your rank list, looks at your remaining token budget for the LLM prompt, and just trims the fat. It selects the top 3 or 4 results, discards the rest, and finally passes that constructed prompt to the model.
Okay, as an engineer, I have to push back on this architecture a bit.
Go for it.
Every single time you add a step query, expansion, vector embedding, a secondary ranking model, you add latency and complexity.
You do.
For a user interface, adding 2 seconds of retrieval latency makes the app feel completely broken. Plus, just looking at it, a 5-stage pipeline looks like an absolute nightmare of compounding errors. Is this level of complexity actually viable in production?
Well, you have just identified the exact reason why our AI systems fail in production.
Really?
Yeah, because it is highly sensitive to compounding degradation. Think of the pipeline as a series of multipliers.
Okay.
If your query processing is 90% accurate, and your embedding model captures 90% of the intent.
And your search algorithm retrieves the right document 90% of the time.
Right. You aren't getting a 90% accurate result at the end. You are getting 90% of 90% of 90%.
Wow. Okay, so the errors cascade completely down the chain. If the query processing slightly misinterprets a word, the embedding is entirely off target.
Exactly.
Because the embedding is off, the search pulls up a vaguely related but totally incorrect document, which means the ranking system puts garbage at the top of the list.
And then by the selection phase, you are injecting perfectly formatted, highly competent nonsense directly into your LLM's prompt.
Which results in a catastrophic hallucination.
Precisely. You literally cannot just slap an API wrapper on a vector database and expect it to work in the real world. You have to monitor, evaluate, and optimize every discrete step of that pipeline.
Okay, so the pipeline has to be incredibly rigorous because we are bottlenecked by the context window. But that actually leads to another fundamental problem.
Which is,
Before the pipeline can even search the documents, those documents have to actually be stored in the database. You don't just embed an entire 500-page manual as a single vector, right?
Right.
You have to chop the data up into pieces.
yes, this is chunking strategy.
Mm-hmm.
It is arguably the most consequential design decision you will ever make when building the storage layer of a RAG system.
The storage layer, right?
Yeah, you are taking raw data and breaking it into manageable chunks. And it introduces what is known as the Goldilocks problem of retrieval.
The constant war between precision and context.
Exactly.
Let's actually look at the extremes of that. Say you chunk your database at the sentence level. Very, very small pieces.
Okay.
The search retrieval will be incredibly precise. If I search for network protocol error, it will find the exact sentence with those exact words.
Right, it'll hit it dead on.
But when that tiny chunk gets passed to the LLM, it just reads, the network protocol error occurs when this happens. The LLM has zero surrounding context. It doesn't know what this refers to or what module we're even troubleshooting. It is a precise hit, but the model is totally blind.
Yes. And on the flip side, say you decide to make the chunks massive. You make every chunk an entire 10-page chapter.
Right.
Now, when it reaches the LLM, the model has all the context in the world. But that massive 10-page chunk covers so many different topics that its overall semantic meaning gets completely diluted in the vector space.
Ah, so it gets blurry.
Exactly. The search algorithm can't find it precisely because the vector is just a blurry average of 50 different subjects. Plus, obviously, shoving 10 pages into the prompt for a simple question will blow through your token budget instantly.
You know, it is the exact same dilemma as deciding the scope of a function in software engineering.
Oh, that's a perfect analogy.
If the scope is too small, the function is totally useless on its own, and you have to chain 100 of them together to get anything done. If the scope is too large, it is a bloated, monolithic mess that is completely impossible to debug.
Yep. Finding that optimal chunk size requires deeply understanding the underlying structure of your data. Like, are you parsing legal contracts, medical records, Python code?
Because code might need to be chunked by function definitions, right? But text might be chunked by markdown headers.
Exactly.
And what about the boundaries? If you just blindly chop a document every 500 tokens, you are inevitably going to slice a crucial if statement or a vital paragraph right in half.
Oh, it happens all the time.
The answer gets split across two chunks, and the search might only retrieve one of them.
Which is exactly why advanced systems use overlapping chunks.
Overlapping.
Yeah, you create a sliding window. So chunk A is tokens 1 through 500. Chunk B doesn't start at 500 to 1. It actually starts at 450 and goes to 950.
Oh, I see.
That 50 token overlap basically ensures that no critical thought or logic block gets cleanly severed at the boundary line.
Okay, so we've architected the system. We have sliding window chunking, we've got a tuned 5-stage pipeline with cross-encoder ranking, and we're dynamically injecting context.
We've got a solid build.
We do. But taking a step back, I have to ask the ultimate architectural question.
Let's hear it.
Why are we doing all this? I mean, why maintain a massive external database and eat the latency of all these retrieval steps when we could literally just bake the knowledge into the model itself? Why not just take our proprietary documents and fine-tune an open-source LLM?
Ah, the RO versus fine-tuning debate. It is literally the crossroads every single AI architect eventually hits.
It seems like the obvious alternative.
It does, but if we look at the mechanics, they solve fundamentally different problems. Let's look at where RO actually dominates. Based on the data, it wins on freshness, attribution, scale, and factual accuracy.
Well, freshness is straightforward. If a developer changes an API endpoint today in our RX system, you just update the database row. The very next user query gets the new correct info.
Instantly.
But if you rely on a fine-tuned model, changing a single fact means you have to kick off an entire retraining job, which costs a ton of time and compute.
Exactly. And attribution is just as vital, especially in enterprise environments.
Mm-hmm.
In RAG, because you retrieve a specific chunk of text, you can tell the user exactly where the answer came from.
Right, you can surface a link that says, source HR handbook section 4.
Yes. A fine-tuned model blends all its knowledge into its neural weights. It cannot reliably point to a source document. It just generates text that sounds statistically correct.
Which is terrifying. If you're building like a diagnostic tool for doctors or a contract reviewer for lawyers, a lack of attribution is a total non-starter. They need to see the receipts.
100%. And then there is scale. Fine-tuning a model on terabytes of specific, dense facts is notoriously difficult. It almost always leads to catastrophic forgetting.
Wait, catastrophic forgetting?
Yeah, you train the model on a massive new proprietary database, and suddenly its neural weights shift so much that it just forgets how to write a basic SQL query, or its baseline grammar just degrades.
Wow.
Yeah. Argy lets you hold terabytes of text in the database without altering the underlying intelligence of the model at all.
But fine-tuning isn't completely obsolete, right? Here's where it gets really interesting. Where does fine-tuning actually win?
Well, fine-tuning wins when you care about style, formatting, reasoning patterns, and latency.
Style and formatting.
Yeah. If you need your AI to consistently output complex JSON arrays in a highly specific proprietary schema, Argy will really struggle to do that consistently. RAG feeds facts, but fine-tuning bakes desired behaviors directly into the model's instincts.
You are teaching it how to speak and how to process information.
Exactly. And the latency advantage is huge. A fine-tuned model just receives the prompt and immediately begins generating tokens.
It doesn't have to pause, query a database, wait for the network, re-rank results, and then generate.
Right. So in high-frequency environments or real-time voice applications, skipping that retrieval step is pretty much the only way to meet performance requirements.
So we aren't choosing one or the other. In a modern production environment, you actually use both. It is a hybrid architecture.
That is exactly what you do.
You fine-tune a smaller model to teach it your company's tone, your specific coding standards, your formatting requirements, but you keep its factual knowledge completely empty, and you hook it up to a RAG pipeline.
Yes. The fine-tuned model becomes a highly specialized processor, and the RAG pipeline serves as its real-time, easily updatable memory bank.
That hybrid setup sounds incredibly
It
robust,
is the gold standard right now.
but a seasoned engineer knows that knowing the happy path isn't enough. You have to know exactly how the system breaks when it hits the real world.
Oh, and it will break.
Let's dig into the failure modes of the open book exam. When does a properly tuned RAG system completely fail the user?
So there are 4 critical failure modes from the literature that break the user experience: ambiguous queries, multi-hop reasoning, contradictory sources, and retrieval noise.
Okay, ambiguous queries make sense. That happens when a user provides zero context and no amount of query expansion can possibly guess what they mean.
Right, garbage in, garbage out. But multi-hop reasoning is far more insidious.
How does multi-hop actually break the UX? Give me a specific scenario where a standard semantic search just falls apart.
Okay, imagine a user asks your internal dev tool, "Why is my authentication token failing?" To answer that, the system actually has to make a logical leap, a hop.
Okay.
First, it needs to search the server logs to find the specific error code associated with that token. Let's say it finds error 401B.
Hmm.
Then it needs to perform a completely separate second search against the engineering wiki to find the deprecation notice for error 401B.
And a basic RAG pipeline has absolutely no mechanism for that. It takes the entire messy question, why is my auth token failing, embeds it into a single vector, and tries to find one single chunk of text that answers the whole thing.
And it fails because the answer simply isn't stored in one place. The search comes back empty or grabs irrelevant log files. The model, lacking the right context, hallucinates an answer.
So to fix this, you have to engineer agents that can break a question down, execute a search, read the result, and then actually decide to execute a second search based on what they just learned.
Exactly. You need an agentic loop, not just a straight pipeline.
Wow. Okay. Here is another brutal failure mode. Contradictory sources.
Oh, this is a classic enterprise problem.
You have an engineering wiki. Document A, written in 2022, says use API version 1. Document B, written literally last week, says API version 1 is deprecated, use version 2.
Yep.
The user asks which API to use. The pipeline, doing exactly what it was designed to do, retrieves both chunks and just shoves them both into the prompt.
And the LLM is looking at an open book where paragraph 1 completely contradicts paragraph 2. It might freeze, it might apologize, or it might blend the two together and confidently tell the user to implement some completely non-existent version 1.5.
Which is a disaster. So dealing with this requires metadata filtering, right?
It does. You have to pass the timestamp of the documents into the prompt and explicitly instruct the model to prioritize the most recent data.
And finally, retrieval noise. This one seems straightforward. You retrieve 5 chunks. Chunk 3 has the exact code snippet the user needs, but chunks 1, 2, 4, and 5 are just massive blocks of dense, complex, completely irrelevant code.
Right, and the LLM can literally lose the needle in the haystack. The noise of the irrelevant text distracts the attention mechanism of the neural network. It actually misses the correct answer, even though it is physically sitting right there in the prompt.
That is so frustrating.
It is. And this forces us right back to refining our chunking strategy and tightening our cross-encoder ranking to ensure only high-signal data makes it to the final prompt.
Building fault tolerance against multi-hop queries, contradictions, and noise is really what separates a weekend prototype from a real enterprise-grade system.
Without a doubt.
But, there is one massive underlying assumption we've been leaning on this entire time. We keep talking about the database, searching by meaning, and mapping concepts in high-dimensional space. We are completely assuming the storage layer can handle semantic intent at scale.
And standard relational databases definitely can't do that. You cannot just run a basic SQL query for semantic proximity.
Which sets us up perfectly for the next step in this architecture journey. We have to explore the specialized engines that make this semantic search actually possible.
Vector databases.
Yes, vector databases. They are the underlying infrastructure holding this entire R ecosystem together, and understanding how they index and traverse millions of vectors is just a whole different level of system design.
Yeah, if R is the library card, the vector database is the library's massive indexing system, built entirely on advanced linear algebra.
We will dive into that next time, but before you switch back to your IDE tonight, I want to leave you with a thought about where this is all heading.
Okay.
If production systems are increasingly using fine-tuning strictly to dictate style and format, and they rely entirely on external RG pipelines for all their factual knowledge and logic,
Hmm.
at what point does the large language model stop being a brain full of knowledge and start being nothing more than a highly articulate UI layer for your database?
Wow. That really forces us to rethink what the AI actually is. Is it the knowledge or is it just the interface?
Exactly.
Oh.
Keep questioning the architecture, keep building defensively, and we will catch you on the next deep dive.